as I ask a question, don't even look at you. Yes. Any questions from homework? You guys do the homework? Is it really, really easy? Chapter 3? You're like, I wouldn't go that far, Jeff, but I just got nothing to ask you yet. All right, whatever. Okay. So no, not yet. All right. I can't remember. No, that was the other class. Okay. So last time we actually did a lot. Last time, I don't know if you realize that. I can't remember now if we actually wrote down a formula for probability of A or B. I think we did. So at one point I wrote this down. Whew. Right? Okay, cool. And we actually figured that out. We sort of figured out what the rule should be. Right? Because we don't want to double count anybody. So if I count everybody in A and I count everybody in B, I got to subtract anybody I counted twice, which is anybody that's in A and B. So like I said the other day, okay, all the men go vote. All the people with brown shoes go vote. Jeff gets to vote twice. Yes. Nah. No, we better subtract one of Jeff's votes off. Shit. All the men wearing brown shoes, we got to take one of your votes away. You guys understand that? Does that make sense? I mean, it just should make fundamental sense. I don't want to count somebody twice. That throws all my counting off. All right. So what I want to focus on today is what are the other equations that we need, right? So falling back on my favorite way to represent probability problem. We'll make it nice and to the point here. Women, men, yes, no. I like it. So some divisive issue. I'm not even going to try to suggest a possible situation here. You can imagine your own. So if I ask you, let's just remind ourselves how this works. If I ask you, if I pick one person, what's the probability that that person is a woman? How do I piece that together? What do I need to do first, even before I answer any questions? Yeah, get all the totals, because probabilities are all based off of counting what's going on. So how many women are there? 17. How many men are there? 19. How many people said yes? 16. And how many people said no? So how many total people should there be? 36. Good. Nobody say 72, please. Right? 72 would be adding these people to these people. You counted everybody twice. Holy shit. At least you're fair. You give everybody 2 votes, I guess. Let me stop there. Is that cool? So very often I'll give you a chart. I'll give you blank spots on the outside, which is screaming at you. Fill me in, please. Because then once you've got all these to fill in, you can answer any question I throw at you. So what is the probability I pick a woman if I pick somebody blindfolded or walk in this room and I pick somebody? 17 chances to get a woman out of 36 total things that could happen. But things are people, but hey, we'll get over that. They're things. They're made of matter. They're just things.
Is that something a pattern?
Say again?
It says pick away.
Pick one person.
Oh.
Sorry. Those in the back. Pick one person. Because when I start picking 2 people or something, that's going to get a lot more complicated. Yeah. We're not quite there yet. So what's probably I pick a man or somebody who said yes? Kind of creepy with it. I just hear a bunch of whispered numbers, you know. That would be really weird math horror movie. Walk into a room, 17, 47. It's just me.
Wouldn't it be 21?
All right, let's find out. How many men are there? Let's do this a silly way, and then we'll do it a smart way. There's 19 men. How many said yes? How many people said yes? 16. If I add 19 people to 16 people, how many have I counted twice?
2.
Those 2 people. So it's going to be minus 2. Let me stop there for a second. Does that make sense? On the top has to go the total number that matches what I'm looking for. I'm looking for either a dude or somebody who said yes. That's why the number gets bigger than either one, because I'm taking either one. That's the nice bouncer, right? Or is the nice bouncer. But I got to subtract 2 because I counted those people twice. So there's what's it going to definitely be out of?
36.
Now the smart way to do that is to say, all right, there's 19 dudes. How many yes people have I not counted yet? 14. And of course, what's 16 minus 2?
14.
Freaking 4. So the math doesn't give a shit what you do. So this is the formula directly. This is just the fact that I can see what's going on. So something really weird that you never expect to hear a math person say is the formulas sometimes get in your way. If I give you all the situations, you actually don't even want to use the formulas. You just want to count. If I can just count, I don't need the formulas. Why the formulas exist then? For the situations when I can't just count. I need to plug stuff in, then I need a freaking formula to plug stuff in. I don't know if that makes sense. Formulas have to be as general as possible, so they are not always the best way to do something. They are just the thing that is always true. They're not always the best way to do something. Do you guys understand? That's the real truth about formulas in general. Either way you do it, though, you end up with 33 out of 36, which reduces to 11 out of 12, which is what as a decimal or percentage? Who?
91.6.
91.6? Cool. Oh yeah, I keep forgetting. My phone used to be my only calculator. And now look at that bad boy. It's insane. It doesn't work. Hello? No? Sure. Hello? Stop talking to your calculator. Alright, so far so good? So that's an example of that formula, but I didn't really need the formula. I just count 19 people plus the 14 yes people I haven't counted yet. You just get directly to the point. Right? What about this? We still have to investigate what and means formulaically, but we can do a problem with and in it. What's the probability I picked somebody, a woman, and they said no? Gotta be further back. Who to what? What's going to be on the bottom? 36. Do I know anything about the person? I don't know shit about the person. The probability that they are a woman that said no. Woman and they said no, right? Who could it be? Anybody. I don't know anything about them. So it's definitely 36 on the bottom. Out of those 36, how many did both of those things? 3. I like the way I said they did both of those things. They are a woman and they said no, 3 of them. So I love the idea that, I think I did this the other day, and is very often called intersection. It's where those two ideas intersect. 3 out of 3 is 1/12, which is, I don't know, 8.3%. Okay. How are we doing there? So we are going to do a formula for and the people that try to do the formula in that problem and get it wrong almost always. Not always, but almost always. Because it's just so much easier to just look at it and say, oh, that's 3, I can see it. What's the probability that they're a man and they said yes? Yeah, that's that 2. Isn't that the same 2? Who are these 2? They are men and said yes. And that's why I had to subtract them, because I counted them twice when I did men and yes. I counted those twice. So that must be all the men who said yes. And see, look, what's this part of the equation? What's this part of the equation? Freaking and, right? Random Blackford. So 2 people out of 36. Well, you can make a percentage, whatever. Okay. All right. All right, so here's finally here's a more interesting question. You know, like this is interesting enough. What's the probability that I get somebody has said no, given they're a man? So what changes now? What fundamentally changes now? Yeah, the denominator, because I know it's a man, right? I was supposed to say, what do we know? But I just told you. We know it's a man. Given it's a man. I'm not given that they said no. The probability that they said no. Did they say no? No freaking clue. The probability they said no, given that it's a dude, right?
Wouldn't it be 17?
Yeah, what's the meaning on the bottom? Sorry?
19.
19. There's 19 men.
Yeah.
Given that it's a man. So 19 men. Out of those 19 men, how many said no? 17. Let me stop there for a second. You guys see? When I say given as a man, your whole universe now is men. Right? Take that as you will. So you just focus on them. So out of those 19, how many said no? 17 out of 19. Right? You focused your attention on just that one group. So all the numbers are going to come from that one group. Does that? So, and whatever that is a percentage. Actually, what is that as a percentage? 89.4? I got competing. Okay. So help me out. What was the probability? It's just a dude. Just probably as a man. Period. Which is what as a percentage?
52.7.
Yeah, so it's a little more than half. It makes sense. All right, let me stop there for a second. Let me let you guys catch up. So just a little over half of my people in this were men. That makes sense. 19 versus 17, right? So that probability makes total sense. A little more than half. So the probability that somebody's a dude is 52.7. If the person... Oh, I said this the wrong way. Shit. You would do that, Jeff. What's the probability that somebody said no? Did I do that already? No. What's probably somebody would have said no if I picked one person? What's probably they said no? 20 out of 36. All right. You're going to be all right, Jeff. You're going to be fine. What is 20 divided by 36 as a percentage? 50. Okay, so my point still stands true. All right, let me try this again. The probability that anybody said no, 55.5%. The probability that somebody said no, given that they're a dude, did it change at all? The probability somebody said no, period, is 55.5. Given that they're a dude, the probability did what? What did the probability do? Went way up. So would you say that those affect each other? Does your gender, does your answer affect the probability, or does your gender affect the probability of your answer? I'm going to say that eventually correctly. Does that make sense what I just said? If I know you said no, it's more likely you're a dude. Does that mean you have to be a dude? No, it means you're more likely to be a dude. Sort of like this. Now, I'm trying to get us ready for this next big idea, so just go with me for a second. If I saw somebody really far away coming walking towards me, and I'm like, is that a man or a woman? What's the chances it's a man or a woman? What's the probability it's a man? 50%. Now, let me see if you guys can handle this next part. I noticed that they had just gotten off of a Harley Davidson motorcycle. Does the probability it's a man stay at 50%? No, it does what? Increases. Now, I love it. One semester I had a woman yell at me because she drives a Harley. I'm like, I didn't say that women don't ride Harleys. What did I say? I saw them get off a Harley, so the probability as a man went up. Does that make sense by itself? Why? Because who rides Harleys more often? Men. Are you with me? I'm not saying that there are no women that ride Harleys. I'm saying the probability that it's a man goes up if I see that they're coming off of a Harley Davidson motorcycle. Are you guys with me? So those affect each other, those two events. If one of them happens, the probability of the other one changes somehow. I call those dependent events. Does that word make sense? It depends on if this other one happened or not. The probability of this one. I like it. Okay, sort of like your test grade versus the number of beers you had the night before. There might be a change in the probability of how high your test grade is based on if the beers happened the night before. Those are dependent events. All right, I like it. All right. Let's do some more Gibbons off of here, and then we'll develop a formula for Gibbon, and then we'll get deeper into what I just talked about, the dependent stuff, right? So what's the probability that they said, that they're a woman, given that they said yes? Yeah, so given that they said yes, it's going to be out of 16. How many women out of those 16? 14. I like it. And that's whatever now. 87.5. Right? Okay. Yeah, Jeff, you know your A's. Good job. What's the probability of just picking a woman? I think that's the first one we did, right? Yeah, so it's a little less than half, right? 47.3. Is that right? Shit. Oh, I gotta leave. I can't stay in this profession if I can't do simple stuff. Alright. So again, I can ask you the same thing. The probability I pick a woman is a little less than half. But if I knew that the person said yes, the probability it's a woman that I picked suddenly skyrockets, right? Doubles. More, almost doubles. You guys understand? This sounds very important. We do this all the time. And again, right now my head is all about politics. And they always break it down into, all right, who voted for Bernie? What were their demographics? Were they younger or were they older? So given that they were younger, what's the probability they're going to vote for Bernie? Do you see what I'm saying? Does that make sense? Or you do traffic, you figure out, do I need to put a stop sign at this intersection? Well, given that I put a stop sign at intersections like that, well, what did the probability of fatalities or injuries change to? Is it worth it? Did it change by a lot or a little? And some people are like, if it changed in the right direction, just do the damn thing, right? You understand? We do this. These are what's called conditional probabilities. I think I said that earlier, but let's write down conditional probability. On the condition of this, the probability of this might change, but it's just a way to calculate that. Okay, maybe. All right, so real quick, I can't escape cards. So too bad. Cards. There's 4 suits in a deck of cards, right? Everybody knows this. What are those suits? Yeah, hearts, diamonds, spades, clubs, and clovers and balloons, whatever. Lucky charms. How many cards are in each suit? Adults. Some say adults. 13. Because you got how many total? 52. I like it. So are you with me? So how many kings are there? Because there's a king of hearts, king of diamonds, king of spades, king of clubs. Okay, I can stop there. All right, maybe. So if I pick one card, what's the probability that card is a king? Yeah, there's 4 chances to get a king out of 52, which is 1 out of 13, which is whatever percent. I can't remember. I used to know these.
7.6.
Sure. Doesn't sound familiar at all, but I know I used to know them. So what's the probability it's a king given it's a club? All right, let's investigate this. What goes on the bottom now? So I have a deck of cards and I say, well, I picked a card. Look at that. And the probability it's a king is 7.6%. But then I say, oh, let me tell you something about the card. The card is a club. Did I just change the probability it's a king? Well, let's investigate it. If I know it's a club, what goes on the bottom? 13. Because how many things could it be? 13. Guys with me? The only things it could be are ace of clubs, 2 of clubs, 3 of clubs. It's got to be one of the clubs, and how many clubs are there? 13. Out of those 13 clubs, how many are kings?
One.
Holy shit. So did the probability change at all? No. You guys still with me? So these are independent events. Oh man, that makes too much sense, Jeff. That can't be right. Why are they independent? Because one happened and did the other one give a shit? No. King said, I'm still 1 out of 13 chance. Nah. If you think about it, why does it make sense? If I only keep clubs, how many suits did I throw out? So I threw 3/4 of the deck out. How many kings did I throw out? I threw 3/4 of the kings out. So of course the proportion is the same. But how many face cards are there? How many cards have faces on them? The jack, the queen, and the king for each suit. So there's 12. So what's the probability it's a king given that it's a face card? What's your gut tell you? If I tell you it's a face card, the probability it's a king should do what?
1/3.
Okay, that's what the number is. It should get bigger. There should be a higher chance that it's a king now. Because I'm throwing out all the non-face cards and keeping all the kings. So what's going to be at the bottom? 12. Out of those 12 face cards, how many are kings? All 4 of them are still there. They all 4 have faces. So that's a 1/3 chance. So the probability went from 1 out of 13 to 1 out of 3. I pick a card and I say, it's a face card. I'm sorry, I'm trying to be some dorky magician. Right? It's a face card. So you would put some good money on it being a king. You feel a lot more confident it's a king than you did before. Right? It's only 1 out of 13 chance it's a king, but now it's a 1 out of 3 chance. That's better than normal for me. Right? 33.3%. Alright, so what's going on here? First is, let's make a formula for given. Alright, I'm sorry. I love that I put the symbol for given is this line like this. People think that it means divided by, but it's a shorthand for given. So I'm going to try to write the word, but that means given to me. So it's just like knowing 2 languages. So if I write that means given. Does that make sense? I can't remember this book. Do they use that line? Oh yeah, they do. Oh, okay. There's one more thing to like about this book. Let's see. Sorry, I got excited there for a second. So what is a general formula for A given B? Shit. So let's investigate these 2 situations. They're going to help me figure out this formula. In both situations, what went on the bottom? I think I did this. It's still familiar. Maybe I did already?
Yeah.
All right, this is a good review. What went on the bottom? Yeah, the number in B. I like it. So we can that's the probability of B goes on the bottom. The given goes on the bottom. And the only way, oh yeah, that's right. I remember this now because I drew you this picture. If I know that B happened, the only way A could happen is if it's where?
A and B.
A and B. So this is going to be probably A and B. Because why is this a 1 here? Because that's the one card that is a king and a club. But how many cards are king and face cards? All the kings. That's why it's a 4 still on top. So there's our next official formula, is the formula for given. Let me stop there for a second. Alright, maybe. Oh, by the way, let me just tell you this, the plan for the next couple days. Today it's going to be me talking a lot. And then on Thursday, I have a kind of like a practice probability sheet that we're going to spend most of the time working on. You ready? So the next time it will be me talking very little. So it'll average out to a decent amount. Okay. To an acceptable level. God, Joe, shut up. If I do that, what are you going to do? All right. I like this. Okay. So let me focus on some terminology And then I'm going to try to explain to you about and. So what's your gut tell you from that situation that I just erased? In order to be independent events, independence, like banana, sure. Independent. In order to be independent events, what must be true? Well, if B happens, I want you to understand this fundamentally. The probability of A, if they're independent, and what does independent mean? If you're independent from somebody, you don't care about them. In fact, you don't care about them all, so you don't have to show them that you don't care about them, because that would not be independent. Right? I don't even know you. Somebody you don't even know. Fred, that lives over in Chula Vista. You know Fred? No. So you're independent. Whatever Fred does, it doesn't have to do anything to you. Right? Are you with me? Just a little bit? Okay. So if B does happen, should the probability of A change? No. So this will still be the same as what A used to be. That, if I ask you, are A and B independent, you calculate this and you compare it to this. That's all you got to do. If they're the same, they are independent. If they are different, they're dependent. So if this is true, then they are independent. If you know logic, it should actually be an if and only if it's true. This is good enough for them. That's the test for independence. It's crazy. Okay, so that's one thing. So that's what independent means. And then something actually a little easier to consider is something called mutually exclusive. Yes, this book uses that terminology. Right? Yes, sweet. Some other book was saying disjoint and joint, and it was like, good Lord, man. Sounds like it's talking about something else entirely. Mutually exclusive, I love that because it makes total sense. To be exclusive means like an exclusive club only lets certain people in, right? They exclude other people. To be mutually exclusive is they don't let me in and I don't let them in my house. Like, you're going to get my house? Get away. Not like they, hey, let me in. No, sorry, I have to take you down that road. Mutually exclusive means not only will we not let you in, I won't let you in either. So there are two things that don't let each other in. What does that really, really, really mean? So two things that are mutually exclusive would be rocks and rabbits. Are there any rabbits that are also rocks? Now, I have to go to extremes because I used to use dogs and cats, and I don't know if you know this. This is a long time ago, even for you now, but there used to be a cartoon, Cat Dog, where I don't want to think about the biology of the situation. I didn't even know this thing existed. Yeah, anyway. So I gotta go to extremes, and there's no Rabbit Rock cartoon that I know of yet, right? Please, some rabbit that's also a rock. I don't know how that would be a good cartoon.
We'll make one just for you.
Thank you. Submit that. I love it. Maybe it's a character on Rick and Morty. I don't know.
Rick and Morty.
Rick and Morty, come on, see. No, sorry. All right. So mutually exclusive. What does that mean mathematically then? If two mutually exclusive events mean A and B share nothing. So, so another example would be you live in California versus you live in Peru. Can you do both at once? No. I don't care if you have houses in both. You are living in one or the other. Does that make sense? So those are mutually exclusive. Meaning, what's the probability that you live in California and Peru at the same time? Zero. So if A and B are mutually exclusive, the probability of A and B is zero. Only makes sense. There's no overlap. What's the probability I pick an animal up and it's a rabbit and a rock? Zero. Right? In real life. I try the in real life thing, and they're like, you never know, man. Some mad scientist somewhere could be on. Yes?
Maybe a stupid scenario. What if a rabbit is choking on a rock? And you find out.
It's still a rabbit with a rock in it, right? So I wouldn't say, you are a foot. No, you're a person that has a foot. You know what I'm saying? All right. You're not a foot. Or you are not whatever happens to be that you ate for lunch, right? Yes? Sorry. Okay, I can do it. All right, how are we doing? So they're very different things, right? In fact, if you have two mutually exclusive events, they are so dependent, it's crazy. So are you guys okay with the rabbit rocks thing still going? I appreciate the attempt. So if I walk in a room full of rabbits and rocks, and I'm blindfolded, just go with me, and I reach down and pick up something, I should be able to tell. Let's say I have no sense of feeling, all right? I don't know what's happening. I walk in a room and pick up what's the probability, let's say there's 8 rocks and 8 rabbits in a room. I walk in and pick one up, I'm blindfolded, no feeling in my hand. What's the probability it's a rabbit?
50%.
50%. I take my blindfold off and I see it's a rock. What is the probability it's a rabbit now?
0.
0. See, they're totally dependent. If you are mutually exclusive, you are the most dependent you can be. Because given one thing, the other thing has no chance. Does that make sense? Because people get confused about, and that's all I want to say about how these two interact with each other. That's all I'm going to say. Because it really doesn't come up, thank God. It gets a little freaky. But that's fundamentally what happens. This is the most dependent you can be. It kills the chances of the other one. I like it. I like it.